Okay, last time, more or less at the very end, we looked a little bit at the vacuum representation of the Raster algebra, and now I want to tell about this a little bit more. So, namely, I want to tell about such thing as normal order in CFT. So we saw that there is a representation constructed so forgot how we know this. Probably what you see. It was constructed from the Drama module with dimension 0. Factorized by Drama module of dimension 1. So which is generated by the vector L minus 1 acting on the highest weight. So so it was one representation of this vacuum module. So it was a span of this vacuum, then L minus 2 acting on vacuum. What else? L minus 2, L minus 1 acting on vacuum, and so on. And what this presentation what this realization of this vacuum module as some vector space. But this is also identified with another vector space. So it was space of states, and there was a space of operators, which I wrote schematically like span of identity operator, energy momentum tensor, dt, and so on. dt, then d to t, t squared, and so on. And the question is, so it was some vector space of differential polynomials of one of a single dimension 2 operator. So, and the question is, what is t squared, and what are all these higher powers? Or we can ask in other words, which operators correspond. So, what are the operators that correspond to these states in the vacuum module? And we partially know the answer because if we compute L minus 1 to power k acting on some state, then it looks so it works like this. While the L minus 1 to the k L minus 2 acting on vacuum equals to k's derivative of energy momentum tensor. So it's case derivative of y of z L minus 2 0. So it is a decay t. T of that. It's on one side, and on the other side, we can compute this L minus 1 to the k action L minus 2, like so L minus 1 to the k L minus 2 on vacuum equals to L minus 1 to k minus 1. Maybe so. First, it will be 1 times 1 L minus 3 action vacuum equals to L minus 1 to k minus 2 times 1 times 2 L minus 4 action vacuum equals and so on. So probably it will be k k minus 2 factorial. No, k minus 1 factorial. No, maybe even k factorial, right? Yes, it will be k factorial L minus 2 minus k action vacuum. So in this way, we know that L minus 2 minus k corresponds to 1 over k factorial decay t of z. Like this. So this you know, and if you now try to add some other operators, we can try to do this by by some insertions of the contour integrals. So, namely, so what do I want to say? So, for example, let us ask the following thing. What is the image of y of z L minus k1 minus 2, or maybe L minus k minus 2 L minus m minus 2 action vacuum. And the idea here is that it is this mode minus k minus 2 of the sorry, Let us first compute this field sitting at 0. So, mm, so in this case, it will be this operator y of 0 L minus m minus 2 acting on 0. And then we need to insert on top of it the operator that will produce this L. And this can be done like this. It is the integral in dz, or maybe the w over 2 pi I. And now let us check what precise operator do we need to insert. Hmm? Yes. So it should be derivative of this dkt. Well, probably we can just say that it is this 1 over k factorial decay t 1 over k factorial 1 over w 1 over k factorial decay t of w. So let us check if it is true. So decay t of w t of w is sum over L. Oh, so it is a decay of ln over w to n plus 2. So now I want to change this summation index to w to the n space derivative. Oh, and when we integrate this expression with dw over w, it will give precisely uh, precisely k factorial times L minus k minus 2. So integral dw over 2 pi I w this of this decay t of w gives k factorial L minus k minus 2. Yes, so it's really that state that we need, and it is located at 0. But but now let us remember how this and so and this state is dm of t. So we can write that it is integral around 0. Ah, 1 over m factorial. So now it is easy to see how to write this expression around arbitrary point, because everything is a translation invariant, and we can just shift this right hand side mm, to some arbitrary point z. So we have this formula for the state at 0. And now just do this shift. So it will be the integral around z, dw over 2 pi I, 1 over k factorial decay t of w, 1 over m factorial dm t of z over z minus w, right? Hmm? Yes, thank you. Yes, it's true. Okay. Uh, so and now the question is, so it's clear then that if we add more operators, we will have something of this kind. So, uh, we see that in general there is this phenomenon that y of some z operator A acting on state B is given by the integral around z dw over 2 pi I, maybe maybe better to use this notation. some v w v u maybe, so that it doesn't mix with the coordinate. So have something of this kind, and we have this object which can be denoted by curly brackets, and it is denoted this way. Some product of two operators computed at point z is defined as the integral around z, dz over dw over 2 pi I, a of w b of z. So and why so and the question is, why is it called product, not some bilinear operation? So the reason for this is the following. Uh, if we write this product of a times b, so let us take this product on the right hand side, a of w, b of z. So it has some OP, and for this procedure to be well defined, this OP should be single valued around w equals to z. So it will be some sum from for n equals to minus n to infinity. Let me think in which direction. Maybe from n to minus infinity. No, sorry. I forgot precisely the conversion. No, probably it should be like this. So this so there is some OP when w equals to z, and it has some singular part from minus n to minus 1. So it is sum from n equals to minus n to minus 1 b of minus n w minus z to n plus AB0 and so and this depends on the second point plus a regular. Uh, and so this normal product works like this. We take the OP of these two operators, look at its singular part, and remove this completely, and then take the first regular term. So, this regular product of two fields is just zeros apart in so it's the constant term in their OP. And this is defined in any CFT. So before we had a normal product denoted by dots, and it worked for the free boson. But this normal product is defined always.
Shouldn't you put some z minus w in the denominator to get the forward?
No, what do you mean?
If you put in the definition of the normal product.
Oh, sorry. Yes, it is this expression on the right hand side. So sorry. And, so there is some operation of this kind, and using it, we can write that such states. So such states y of z L minus K1. Maybe let me put this factorials in the definition. K1 factorial L minus K1 minus 2 and Kn factorial L minus Kn minus 2 action vacuum. So this equals to d K1 t multiplied by d K2 t multiplied and so on d K n minus 1 t d K n t. So like this. But so it's of course not the only possible order. In a sense, we can multiply them in different ways, but all such expressions can be reduced to this one. Hmm? Hmm. Also, it is clear from this definition that it is something non-trivial. So there is, for example, no reason for it to be commutative. So, so AB is uh, uh, not equal to BA. So simply, if you try to expand this expression around another point, around W, you need to take all the singular part and compute its expansion around W. Also, so there is also no reason for it to be associative. So A, B, C is not equal to A, B, C.
So it's not the same as saying QFT equal to the expression of the integral on one side. One side of the
Oh, in some sense, so it's the next part of the lecture. In a sense, I wanted to make this parallel with QFT. In a sense, it is that procedure, but the difference is that if our algebra is non-commutative, we have a question about positive modes themselves, positive and negative modes, because for the free boson or for the free fermion, positive and negative modes commutes between themselves. But in general situation, for example, even for the Versor algebra, they don't commute, and we have a question about ordering of this positive and negative modes. And this definition fixes some ordering of them. So, yeah, good. Okay, let us try to write some mode expansion of this. Uh, so A B of uh, Z is in this integral around Z. Uh, so let me draw it like this. Uh, 0, there is some point Z, and we have integral in W. The W over 2 pi I is W d of Z over Z minus W. So it can be written as a product of two integrals. One is for absolute value of W greater than absolute value of Z. Mm. Another is for absolute value of W less than absolute value of Z. And we can expand this denominator as a geometric progression in both of these cases. So if absolute value of W is greater, then no, let me think. Ah, oh, it should be W minus Z here. Sorry. Hmm?
Why do you put the minus sign?
Where?
What are these contours we are taking?
And this one and and this one. So originally it was clockwise. Come. So now we expand this geometric progression when absolute value of W is greater than absolute value of Z. It is Z to the N over W to the N plus 1. Of W B of Z. Plus integral the W over 2 pi I. Now it is W to the N over Z to the N plus 1. So, and now remember that all this computations are actually written under the normal ordering. So probably it's better to put on this radial ordering sign everywhere. And so in this case, absolute value of W is greater than absolute value of Z. So this field stands on the left. And we can write that it is integral the W over 2 pi I of W sum hmm.
So we are taking
Let
the
me think.
regular product of the normal constant.
No, what do you mean?
Because that the first piece is what we define as the normal product.
Yes.
Now we are taking the regular.
No, radially ordered. So we need to remember that all such computations are valid only under the radial ordering sign, because it comes from the path integral, and the path integral always gives normally ordered operators, radially ordered operators. Because if we evaluate this radial ordering, we can get some divergent series or delta functions in the best case. So So I'm omitting this sign almost always. But if you want to think about them as about some operators, I can on some space. You should remember that they're ordered. Mm. Mm. So I think maybe it is better to write on this expressions in a little bit different form. Like I want to write it as dw over 2 pi I w f w times this f plus so, um, uh, uh, b of z. Mm. So and we should use this radial ordering here. Saying that B should stand on the right. So, and in the other part, this radial ordering is opposite. So here it is absolute value of W greater than absolute value of Z. Here it's absolute value of W less than absolute value of Z. So here this order will be different. Mm. So there is such kind of expression, and now let us just uh, introduce two operators, b plus and b minus, in the following way. So basically, what we see here, we will call, oh, sorry, not b, but a plus and a minus. We will call this a plus, the summing integral, and that summing integral a minus. So, uh, so it can be written as a plus of no, sorry, maybe not like this. Maybe vice versa. No, yeah, vice versa. This should be called a minus of z, a times b of z, and that one is called a plus. Uh, hmm? But who is w? W is an integration variable. Mm, so what was it? Yes, thanks. Yes. Uh, yes.
Now, yes, we put those two pieces under the same integral.
Mm, but well,
So
it doesn't matter.
the first one is for W larger
Mm-hmm. Yes. So so we have this equality, and now let us understand the meaning of this minus and plus. Uh, so a minus of z is defined by the integral dw over 2 pi I w so from n equals to 0 to infinity a of w and a plus of z and the integral dw over 2 pi I w sum from so we can now change summation variable, and this will become from n equals to minus infinity to minus 1 z to the n over w and w to the n a of w. So and now let us remember that a field of dimension delta had the following expression. So a of z is the sum over integers a n over z to n plus delta, delta of a. So, for these purposes, it is better to shift this sum by delta. So it will be written as a sum of a n over z a n minus delta of a divided by z to the n. So, and if you now look at this formulas, can you tell who this a minus and a plus are?
The integrals are around zero.
Yes. Well, this is precisely this integrals. So, let's see. Hmm? Uh, so, could you say it again? Yes, this is just to ensure that the series are convergent. So, but when we switch so when we write that this integral is sum of integrals, it does not matter anymore. Well, in a sense, it kind of matters, but we don't see it. So again, it can be written like this. Mm, no, because hmm? Hmm? So of what?
In this one, because there is EW to buy
No, so the main question is power of this argument of A should be positive, uh, so that we have some chance to get a non-zero expression. So it means that this n should be negative. Yes. So it is. So let me actually think. Mm, uh, hmm?
Can I write it as n going from 0 to infinity of a minus n
Mm, oh, sorry.
Or you could just substitute it in the expression, I guess.
Hmm? What do you mean?
If you want to set
Maybe better to write a of w's because it is easier to substitute it there. So integral of uh, dw over 2 pi I w mm, uh, z to the n over w to the n a of w is so uh, hmm? Mhm. Yes. So if we take no, it was also multiplied by z to the n. So this sum will be from for n equals to 0 mm, to infinity a minus n minus delta of a d to the n, and this will be sum from n equals to minus infinity to minus 1, and we can also shift this summation index. So if we denote this by nu n, it will change from n equals to minus infinity to minus delta of a, 0 to n plus delta of a. And this will go from n equals to minus delta of a plus 1 to infinity. A n or z n plus delta of a. So, are there any questions on this? And there are examples. If if delta of a equals to 1, for example, a equals a equals to this current j, then so j minus will be j minus of z will be in this sum from n equals to minus infinity to minus 1 jn over z to n plus 1. So it is j minus 1 plus z j minus 2 plus z squared and so on. And j plus is everything else. So there is in this example. Oh, yeah. So there is also this example which is studied here for the energy momentum tensor, and it is for delta of a equals to 2. So this is a equal to t. So t minus of z will be sum for n equals to minus infinity to minus 2 ln over z n plus 2. So it starts from L minus 2 plus z L minus 3 plus and so on. And the t plus of z is L minus 3 is L minus 1 plus so Z inverse L minus 1, Z minus 2 L0 plus 1 plus other terms. So, and the analogous situation is for the other terms, in the sense that if it is some field of dimension delta, its positive, so its negative component starts from the constant term, which equals to corresponding negative mode. So it's minus delta's mode of this field, and then some corrections. And positive mode, positive part contains everything else. So we can write that for arbitrary a delta, it looks like a minus of z equals to a minus delta of a. And it is more or less clear if we try to write such expression. So, for example, if we try to write this normal product and act and move this z to 0. For example, for this energy momentum tensor. So I, I don't know, maybe it's some trivial example. I think. Maybe Maybe I'm forgetting to say something about this formula, but uh, uh, I don't remember what can be what else can be said. So there is this normal product, and we see that if this so uh, we see that if this B of z can be written as well, so B of z can always be written also this sum of positive and negative modes, and if positive commutes with positive, negative commutes with negative, this is equivalent to usual bosonic normal ordering. For example, like in this case. So this J0 is sent to J plus, but apart from this, it is some standard separation into positive and negative modes. Mm. Unlike this case. And mm, so in this case, it is equivalent. But for example, let us try to compute the difference between bosonic normal order and this one. Mm, mm. So let us try to compute normal this regular product of T and J at point Z. Oh, so to do this, we need to compute the OP. T of W, J of Z. Uh, no, J of oh, sorry, it should be written explicitly. So we have one half of usual bosonic normal order in GFW, GFW, GFZ, and it equals to one half GFW 1 over Z minus W W minus Z squared. That's all. No, plus normal ordering of everything. So now we need to expand this around Z. Computation that we actually did at some moment. So without one half, because there are two parents. It will be J of Z or W minus Z squared plus D J of Z or W minus Z plus so this one can also be expanded around Z. So it is regular, and I can do it immediately. So J of Z cubed. So if we look at this formula, we conclude immediately that normal product of T with J Z equals to this 1/2 J of Z cubed plus 1/2 D2 J of Z. Well, the second term does not need ordering. So there are different expressions. And if we try to compute it in opposite order, so it will be J of it will be 1 over W minus Z squared J of Z plus normal product of J of 1/2 and J of Z cubed plus regular. So what does it equal to? So what does this regular product equal to in terms of bosonic normal ordering? Sorry. I'm no, I'm writing the OP and call it a regular product. So it is J of W T of Z. So what is an NTR? Is it clear now? Hmm? No, it's the end of this computation. So we computed this normal product T with J. Question is, what about this other one? Uh-huh. Yes. And so we see that, of course, all these normal orderings are related because all of them can be used to construct some regular operators to write some explicit form of the OP. Uh, but so they are related, but they don't coincide. And this one, which is defined from the OP, is something universal in the sense it does not know about explicit realization of these fields. Uh, and this bosonic normal ordering knows about the internal structure, so it knows that something is g of z squared. And if we instead use some fermionic realization, then a fermionic normal ordering will know about some different fermionic structure of the operator and give some different answer. So, mm, so in some sense, it is not universal. So there can be a lot of this bosonic, fermionic normal orderings that depend on the basic field which is used to construct everything. And this one is something unique. It exists in any vertex operator algebra, even if it does not have a fulfilled representation. So, are there any questions? This? No, it's not like they just don't commute. So for example, here we can say that it is the same as a normal product of tj of z, because this bosonic normal order and simply moves all positive generators to the left, and this one does not equal to t j. Maybe we can write it as t of z, j of z, t of z, j of z. So uh, probably people actually study this non-commutativity and non-associativity of this regular product, but I don't know how useful it is because after all, uh, uh, some computations are easier to do in uh, as computations with first non-trivial modes of this algebra rather than computing this OPs at arbitrary point. So let me maybe show some examples later. Uh, and now I wanted to also try some formula for some uh, example of such operators with this normal ordering. So, namely, let us look at the operator as a square of t. Let us look at its mode expansion. There is this operator tt of z, which corresponds to L minus 2 squared. So it is a y of maybe something like, yes, L minus 2 squared. So it should equal to sum from n equals uh, to minus infinity to minus 2 L minus 2 over z to n plus 2 no L n L m over z to n plus 2 for positive and negative n's. So this operator mm, we should invent some name for this. Let us maybe call this T2. Or just T squared. K over Z K plus 4. Because it's of dimension 4. And let us try to write some formulas for the coefficients of this TKs. TK squared. Oh. We can just express m in terms of n, so it will be sum from n equals to minus infinity to minus 2 ln over ln ln l k minus m plus n. Sorry. M is k minus n. K minus n l n. So I see that on this term starts, so this term is almost normally ordered. In a sense, it starts from L minus 1. Mm. And this term in principle can require some normal ordering because this k minus n can be negative. Oh, no. So let me think. So if this k is negative, then lk minus n can be negative. But, actually, oh, maybe it is not very interesting to try to reorder such terms. We see at least that if we want some particular mode, and if we want to act with this mode on something, then we should do some some reordering. But let us try to ask some more practical question, like let us ask how to perform reorderings in the general situation. So for example, we know that there are expressions like t, t, t that correspond of z, which correspond to um, L minus 2 cubed action vacuum, like this. And let us ask about such expression, like what is this? So in principle, we could do some uh, computation with the computations with this infinite sums, but since we work with the operator algebra, we can write simply that it is the result of application of this mm, uh, operator to the state generated by a single L minus 2. So we can write that it is this t squared. What mode of it? So what mode should we take? Hmm? Yes, yes. L minus 4 acting on L minus 2 on vacuum. So now it is some practical question to find a minus fourth mode of this operator and then apply to the state. And let us do this. T2 minus 4 equals to sum from n equals to minus infinity to minus 2 n minus 4 minus n So we should be interested in the terms which don't commute with L minus 2. So the so if there is some, for example, um, Now there is, for example, some L3 there. Then we have a state of dimension -1, which cannot appear in this module. And also, if we have some operator of how to say it. So if you have if you act on the state with L1, it will be 0 since L minus 1 kills vacuum. If you act with L 3 and higher, we get 0 because there are no states of negative dimension. So we should be interested in the operators that have L2 on the right and negative L's. 0 and also uh, 0, yeah, 0 and all negatives. So let me just write a few terms which are here. So starting from L equals to -2. There's L minus 2 plus L minus 1 L minus 3 plus L0 L minus 4 no, sorry, I went into the wrong direction. So, no, it is L minus 3 L minus 1 3 L minus 1 this is L minus 4 L0, which is fine, plus L minus 5 L1. So this term will act by 0 because it will produce L minus 1. So then we also have L minus 6 L0, which acts somehow. Mm, Hmm? No, sorry, I wrote something. No, it's L2. It acts by 0. Oh, well, I probably will not cancel it here. I will just say it later. O minus 5, O minus 1, minus 5, L1. So it is plus something else, but starting from L1, they act by 0. Plus, and now we write this second term. N equals to -1 and gives L minus 3 L minus 1 plus so now they go up. It is L minus 4 L1 L0 plus L minus 5 L1 plus L minus 6 L2 plus the other terms. Yes. So let me think. If everything is correct, probably it's fine. Okay, so taking all this together, so it's L minus 2 squared plus on this term appears twice. Basically all of them appear twice. Plus everything else. So now let us act with this operator on the state L minus 2. So this state is just L minus 2 cubed. So here it's nothing interesting. This state L minus 3 L minus 1 L minus 2 0. Well, in principle, it cannot be left as is because we need to commute this L minus 1 as the L minus 2, and it will be just 2 L minus 3 squared acting on 0. Then this L minus what minus 4 L 0. Here we will have this commutator which gives 2. So it will be 4 L minus 4 0. L minus 5 L1 L minus 2 0. So what does it equal to? What do you think? And because it is 2L minus 5 times 3L minus 1, 0, which is 0.
So should there be some
Hmm?
some minus
Yes, thank you. Hmm? Yes. Mm. So this is 0, and the last term 2L minus 6 L2 L2 L minus 2 0 will be 2L minus 6, and now we use this commutation relation. C 8 minus 2 over 12 plus 4 L0 actual vacuum. So it will be C L minus 6 actual vacuum. Right? So if we now take all this together, we see that this regular product of T with T of Z equals to what? It is first this product right in this form, product with this order, and then this term is what? It is dt squared dt of Z plus so here we have actually times 2. Here we have 2 d2t dt no, it's d cubed. Oh yeah, no, it's d2t. So in this last term is something like 1 over c over well, it's false derivative, so it's c over 24 d 4t. So it's sum of some operators of dimension 6. But the main message of this computation is that it is something that defined that is defined in in the space so in some infinite dimensional space, in a sense, we can understand this normal ordered products in this kind of QFT like normal order, and when we take positive parts of series, negative parts of series, place them in some way, and then we need to reorder this semi-infinite series to go from the left-hand side to the right-hand side. It can be done this way. right? But since we work in the uh, vertex operator algebra, such in principle infinite computations with uh, 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 so what do I want to say? So such computations with semi-infinite series can be replaced by finite computation with just a few terms in this expansion. So what I'm saying here is the following, that in principle this computation is equivalent to something like this. So let us write this normal product. So it will be so we will have T2 K oh, to write it better. So we have two K, which is given by this T. Oh, have T2 of Z, which is equal to T minus of Z, T of Z plus T of Z, T plus of Z. And we have this normal ordering, which is to say that T2 minus times T plus T times T2 plus equals to this opposite product. So it is T minus T2 plus T 2T plus all these other terms. So there are some computations with double infinite sums, and in principle they are doable, but quite unpleasant. And this computation you saw, it was very simple, and actually, such a trick that we can pass to computation around zero, which is just some computation in the algebra without all this infinite series. So this trick can be used not only to compute some regular product, but also to compute some commutators, because here we computed just zeros order in the OP of the two operators, A of Z, B of W. But let us try to think what happens if we take some derivative. Uh, No, maybe. What do I want to do? Oh. So in this computation, we did what? We took t squared of z and computed its action on the state. So we computed its OP with t of z, which is this state, L minus 2. Yeah, but in principle, we have this full OP. So we have some from, in principle, n equals to z, some from n equals to something, to infinity, y uh, of 0, t squared k, l minus 2, 0, z to minus k minus 2. So we have this on one side, and so it's just by definition. And on the other side, we can write that this t2 of z, t of t of 0 is a sum from n equals to minus n to to oh, sorry, I wrote no, it should be minus 4, since it has dimension 4. Yes, thanks. From k equals to minus n to, so here we need to take the sum till 4. I missed the order of summation, so it should be from k equals to n to minus infinity, from minus infinity to n. So this should be sum from k equals to minus 3 to some n plus a regular. So that first term which we computed corresponds to the regular product, but this OP also contains singular terms from minus 3 to n, and let us actually think what z to minus k minus 4. Let us think about the value of n. Mm, so it should be something uh, mm, that so it looks like k equals to 2 is is the upper bound. Because let us look at T2 squared. It is we should probably look at. No, actually, I, I don't remember, and I don't want to do this computation now. But we can estimate the order of singularity. Well, maybe actually it's some uh, just 0, because if we try to do some computation in the free theory, then there are these two j's which correspond to t of 0, and the only singularity will be 1 over z minus w. No, not necessary. That they can have derivatives. So probably in the general situation, this sum can go to 2. So the point is that we have such a computation of this kind where each term is given by some finite computation of this form. We just take some first terms of this infinite sums, because all other terms act by 0 act on some vector in this Varma module, and expand it in the basis that we have. And in this way, we get a singular part of the OP, and a singular part of the OP will lead to the computation relations between these components of t squared, okay, with the Virasoro generators. So our profit is the following: we had some formula that contains infinite series in n, and we now are able to commute it with a single L without taking these infinite sums. Also, we could write here O minus 2 squared, and in this case, this situation for naive computations, so we can write this, for example. Then it will be OP of T2 with T2. Uh, so here we will have t squared, t squared m. So here it looks like we need to compute some commutator of two infinite sums, which is in principle computable, but very hard. And it's unclear how to make it, how to do this automatically. But such computation is just some computation in the algebra. So, and I hope we will use such kind of technique to compute computation relations in the Cosmode algebra. Because, of course, it can be done just by commuting this series, but there are more efficient ways to do this. And if you work with the infinite series, it's not even obvious from the beginning that we can sum everything just to some operators of this kind. But using this operator state correspondence, we have a guarantee that we get some state in this vector space, and so it automatically corresponds to some operator of this form. In some sense, all this encodes a simplified structure of such series in the sense that they don't contain any unknown functions. They only contain sums with a fixed sum of all indices, and also with some coefficients like powers of n, n's powers of k's, in case if it takes some derivative here. Okay, are there any questions about this? Okay, thanks for your attention. See you on Thursday.